Today, we're presenting our work on volumetric image classification for rectal cancer staging. Rectal cancer is a cancer that begins in the rectum, which is the continuation of the sigmoid colon before anus, as illustrated in this figure. T categorization quantizes the severity of rectal cancer by the degree of the tumor invasion into the rectal wall. Among other tasks, the discrimination between T2 and T3 staging is arguably the most challenging yet clinically significant task, since it determines whether to use chemo-radiotherapy to patient, a physically burdensome and costly treatment option. Therefore, in this study, we propose a network to accurately discriminate T2 from T3 stage rectal ML volumes. Here is the overall scheme of our method to discriminate T2 from T3 stage rectal ML volume. Our proposed network consists of the volume encoder and the depth aggregation function. I'll first explain about our volume encoder. For a volumetric medical image analysis, there is an open problem on whether to use 2D CNN or 3D CNN. This problem arises due to the large anisotropy of medical volume, which is the large resolution gap between z-axis and that of x and y's. Specifically, the large anisotropy discourages the use of the isotropic 3D convolution kernel, though 2D CNN completely discards the inner slice information. To handle this problem, we propose various mixtures of 2D and 3D CNN, motivated by video classification community. Next, I'll explain about our slice level training, how we can prove if adjacent slice information helps learning. With a full 2D CNN, two slices from a single volume can be separately mapped into their respective probabilities. This approach makes no interaction between slices. However, because we want to find if adjacent slice information helps learning, we use all consecutive slices within a volume. Though each slice will have its corresponding probability, we only use the probabilities from the representative slice for training, which is a slice which has its class label. Motivated by the video classification community, we mix 2D and 3D CNN following either early fusion or late fusion strategy. This figure illustrates the selected late fusion network and how we train it using the representative slices. Note that the adjacent slice interaction occurs at the last CNN layer in this example. Now I will explain about the depth aggregation function. The depth aggregation function aims to merge the slice level feature into the volume level. In addition to the widely adopted global average pooling, we also compare the performance of max pooling, bilinear pooling, and the attention weighting. This is a whole network scheme with depth aggregation function. We show the performances of the full 2D, 3D CNN and their mixtures using tenfold cross-validation and select the network based on the AUC. Our full 2D CNN scored the second highest AUC, whereas a full 3D CNN scores lower than the full 2D CNN and all the late fusion variants. The 2+1D CNN, which is widely adopted in the video community, did not score high performance in medical volume. The early fusion did not score high either. The figure at the right side here is an exemplary early fusion network. The index 3 of FMC3 here. This figure refers to the index of layer in ResNet-18 where the convolution type change occurs. The late fusion method, FRMC5, scored the best performance among all networks. The only difference between FRMC5 and the full 2D CNN is the last convolution layer, which is this. Next, we evaluate the performance of various depth aggregation functions. The bilinear pooling function outperforms all other pooling functions. We assume that the nature of cancer classification shares similarity with fine-grained image recognition, in that the severity score of a cancer image is determined by the subtle portion of a sample. Note that the bilinear pooling function greatly reduced the gap between the recall of T2 and T3 compared to other pooling functions. In conclusion, we propose a CNN model to accurately discriminate between T2 and T3 stage rectal ML volume, which is arguably the most challenging yet clinically significant task in treatment planning. Specifically, we showed that the late fusion method and bilinear pooling function outperformed all other 2D and 3D CNN mixtures and depth aggregation function respectively. Thank you very much.